Okay, we're looking at trends in boiling points across periods now. The ones that they're going to ask you about in the exam will be period 2 and 3. So we don't really look at the transition metals, so just period 2 and 3. So for example, here's period 3. And you often see, you always see this pattern, that here we've got sodium, magnesium and aluminium. They're the three metals, group 1, group 2, group 3. And you can see there's a general trend going from sodium to aluminium of it increasing. Group 4 is also high, in this case we've got silicon. And then there's a massive drop down to phosphorus in group 5. So group 5, 6, 7, and 8 or 0 are always very, very low. Okay? So 1 to 4 start off fairly high, increasing to high up here. And there was a dramatic drop from 5, 6, 7 to 8. Okay? So why is that? Well, depending on what period you're looking at, there's a slight difference between 2 and 3. This is period 2, along here is period 3. In group 1 and group 2, here are always metals. So they have giant metallic structure. There's a strong electrostatic attraction between opposite charges of the positive ions and the delocalized electrons. Okay. Now aluminium is a metal, but boron isn't. So here we've got metallic, metallic, metallic in period 3, so metallic, metallic, metallic. In period 2 you'd have metallic, metallic, and then boron is actually giant covalent. Okay, so watch out for that. In this example here, silicon's giant covalent. Carbon we know is giant covalent, that's like graphite and diamond. So they're the three that could be giant covalent. So giant covalent is also a strong, also has strong bonds that have to be broken, strong covalent bonds. So in a giant covalent structure, to be able to melt it and boil it, you have to break strong covalent bonds. So that's always high in silicon, graphite, diamonds, as in carbon, and in boron. Those three will always be high as well. It takes a lot of energy to break those covalent bonds. The dramatic drop to group 5 is because then we go into molecular structures, simple molecular. Okay, so the numbers here represent the type of molecule that these elements form. So phosphorus goes around as P4, 4 phosphoruses together, or nitrogen would be N2. We've got S8, Cl2, Ar for argon. So the group 8 or 0 are always single atoms, monoatomic, they don't bond to other things. So there's always a slight variation here. Sulfur, it's slightly higher than phosphorus. The reason for that is because there's actually 8 sulfurs per molecule. And van der Waals forces, which are the weak forces of attraction between the molecules, the strength of those are controlled by the number of electrons in that molecule. So because it's S8, it's 8 sulfurs, there's more electrons in sulfur than there is phosphorus. As we go across because there's only monoatomic, although argon itself has more electrons, there's only one of it, its boiling point's very, very low. Okay, so when you're describing the pattern, the boiling points or melting points across a period, think of the type of bonding. Remember, group 1, 2 and 3 will be metals. If it's period 3, it will just group 1 and 2 if it's period 2. Giant covalent bonding, look out for them in group 4 and group 3 if it's in period 2. And then we got, from period 5 onwards, we've always got simple molecular or simple covalent. We should just be talking about weak forces. So here, energy is only needed to overcome weak forces of attraction, or the van der Waals forces. Here, with the giant covalent, we've got to break strong covalent bonds, and with the metallic bonding, we've got to overcome the electrostatic attraction between metal ions and the delocalized electrons, and that gives us our pattern. So always think about the type of bonding and the forces or bonding that has to be broken in the melting and boiling process.